as I've been saying for a little bit, whenever you're writing programs, obviously writing the code for your program is a big part of what you have to do. But a bigger part of what you have to do is debug what you did wrong, because you will invariably be making mistakes. That's not a jab or anything, that's just a matter of fact. No one sits down and writes perfect code the first time. And the other half of it, it's not only that like, oh, it ran, good. It's about making sure it's correct. If I say write a function to do X, Y, Z, and you're like, here, I wrote it, but if it's wrong, what good is it? It's absolutely useless. It's not correct. So we want to test our code. And so far, you saw we were testing our code, right? We were doing things like, well, Celsius to Fahrenheit. Let's see what happens if we put in 0. What's -40? That type of stuff. Little quick tests for our sanity to know, okay, yeah, it seems to be working. They weren't particularly thorough, but they were, enough to make us comfortable that nothing is going way too wrong, right? If you're a programmer and you're writing code, you want to be perhaps a little bit more systematic in this. And we write code, we write functions to automate something, right? I don't want to calculate Celsius to Fahrenheit. I want to write a program to do that for me. Great, so you've automated it. We can automate the process of testing our code as well. There are a couple of ways we could go about doing this. There are correct ways to go about doing it, but to start, because we're all brand new at this, we're going to start with a very simple way of ensuring our functions are correct. And I will say, there is no way to guarantee that your function is correct with the tests like I'm going to show you. They're not going to guarantee it's correct. Just because your function passes all the tests, it doesn't mean that necessarily it must be correct. It means that you're pretty damn sure it's correct, right? So just be warned that there's no guarantee here. Once we write a function, often we want to run it a couple of times to make sure it seems to be working the right way, but we want to be a little bit more systematic in how we do it. So what we do is we write little chunks of code designed to test our code. And then if you're going to say, well, do we write code to test the testing code? Well, no, we draw the line somewhere. We'll write little pieces of code to make sure, to run our functions to help us know if it's correct. For simplicity, we're going to be using assert. Assert is a special keyword in Python that if you call it assert, if you say, I want to assert that the number 5 is the result of calling the function with this input. I want to assert that Celsius to Fahrenheit, if I give 0 degrees Celsius, I'm going to assert that the result better be 32. And if you run that line of code and it's correct, nothing will happen. If you run that line of code and your function gives back a different number that's not 32, your code will crash. It'll say assertion failed. That's how we can know if our functions are passing our tests or not. To start, I'm going to be writing some tests, some assertion tests, for the absolute value function. The absolute value function is a function that's already provided to us. There is no reason we would be testing this in reality. We could be pretty darn certain that, if Python gave us an absolute value function, it's going to be correct. But for demonstrating how things work, we're going to use that to start. For those of you that don't remember, absolute value is a very simple function. All it does is it'll give the positive version of any integer you give it. So if I give it the number 5, it just gives me 5 back. If I give it the number -7, it gives me positive 7 back. That's how absolute value works. So we can test it with assertions. We want to make sure we're thorough, though. With absolute value, there's really not a lot that we might want to test. I want to test that if I give it a positive number, it gives me a positive number back. That's the right number. If it's a negative number, it gives me the right number back, the positive. And I guess the funny little peculiar case might be 0. Because 0 doesn't have like a sign, right? So absolute value of 0 should just still be 0. That might be what we would call, arguably, like, we call these little scenarios edge cases, where, you know, your general purpose absolute value, you know how it works. But then someone might come along, yeah, but what happens when it's 0? And you go like, yeah, that is a funny case. That's what we would call an edge case. And they're important things to test for. A lot of times, those are the tricky things to test for. Yeah, checking 0 is perhaps not necessary, but it's somewhat of a peculiar case. So here's how I would test absolute value. Here's 3 lines of code. Assert that 5 is what I get if I call absolute value of 5. Now, notice, I'm making use of that comparison operator we talked about yesterday. Equals equals. That's going to return true. So really, assert will pass if the final thing that gets crunched down to is a true. Assert true, assert true. If it ever gets a false, if you ever write assert false, your program crashes. Any statement that's false, it'll crash. So assert that 5 equals absolute value of 5. Great. If you don't like that order, if you like to think like, well, no, why wouldn't I do the function call and then equals 5 because it makes more sense to you naturally, that's fine. The order doesn't matter. It doesn't matter that I put 5 on the left-hand side and absolute 5 on the right. It could be vice versa, just as long as you're consistent, that's all that really matters. So the absolute value of 5 better be positive 5. The absolute value of negative 5 better be positive 5, and the absolute value of 0 better be 0. If I run that code, I expect to see no output. Got to connect, give it a second. Wow, this is taking a while. There, I ran it. We see nothing here, because everything was fine. Now, for the fun of it, I'm going to write a test that's going to fail. Because if I say the absolute value of 5, oh, it better be 15, obviously that's not correct. This is an error with my test. But I just added it here to show you what happens if a test were to fail. So obviously we know absolute value of negative 5 is not positive 15. We run it, it says assertion failed. Right here, that line, negative 5, absolute value of negative 5 is not 15. And then I look at that and go like, oh yeah, it's because I wrote my test wrong. There's nothing wrong with the absolute value function, it was my test that was wrong. So I run it, great. For demonstration purposes, I'm going to write my own absolute value function called broken absolute value. If you look at this function, it is a remarkably simple function. You give it x, it gives you x right back. That's it. You give it positive 5, it gives you positive 5. You give it negative 5, it gives you positive, or no, it gives you negative 5. It's the broken absolute value function. We all know that is not the correct absolute value function. It's wrong. But I did that intentionally to show you what happens if your function is wrong. So pretend for a second we wrote this function, and we think it's correct. We missed the fact that we've got a bug in our code. I know, we all know there's a bug there, but let's pretend we don't. I write the test going like, well, okay, absolute of 5 should be 5, absolute negative 5 should be positive 5, and absolute 0 should be positive 0. So now there's no issues with my tests. The tests are great. The issue is with the function I wrote. I hit run, and it fails. Why? Well, because here's what I would look at. I would say, oh, my goodness, well, my function that I wrote failed on absolute of negative 5, and it gave me back, it didn't give me back 5. So now it gives me an idea of where the problem might be. Like, on that input, it gave me the wrong output. What's up with that? So it helps not only guarantee that your functions are correct, your assertions run, great, you're happy. But when they fail, they help guide you in what's wrong. Any questions so far about these assertions? Okay. Yeah, if we run the code, we'll see an error like this, assertion error. This is Python telling us the assertion failed. More precisely, it failed on the input negative 5, and we can see. This now informs us the function is not correct and under which conditions it's not correct. So if we go back and look at a function we talked about in the functions topic called square of sum, this is the correct function. And of course, now you will notice I've got that docstring comment, right? Like we talked about in the functions topic, and we always add those. So calculate the square of the sum of the two provided inputs. So add the two inputs together and square it. So 2 plus 3, this is the example. 2 plus 3 is 5. You square it, you get 25. Parameters, return, whatever. Here's the function itself. It looks correct, but maybe it's not. To help prove to yourself and anyone else who would look at your code, you write the tests. Okay, so here's a couple of tests. Sum of square of 0, 0 should be 0, right? I know this. If you add 0 and 0 and square 0, you get 0. Sum of square of 1, negative 1, well, 1 plus negative 1 is 0. You square 0, it's 0. So on that input, it should give you the output 0 still. If I do 5 and 5, well, 5 plus 5 is 10. 10 squared is 100. Great. And negative 5 plus negative 5 is negative 10. Negative 10 squared is positive 100. And then I have another test down here that looks a little different. I'll talk about that in a moment. But I'm doing 2.2. Now I'm testing it on floating point numbers. All the previous tests are all integers, so why not test it on floating point numbers, because that should work as well, right? Now notice the cases I gave it. There is no way to say those are the correct tests. Yep, your tests are perfect. They're great. The trick with tests is to think about trying to cover as many potential cases as you can, but not going overboard. There's no need to test like, well, what if I give it 1 and 1, and then I give it 2 and 2, and then 3 and 3? Well, you know, if it worked for 3 and 3, presumably it works for 9 and 9, right? There's no reason that shouldn't work. So you come up with reasonable tests, and you'll notice that the 0, 0, I guess, is kind of an edge case. Maybe it's not really an edge case, it's just a case. 0 and 0, you add them together, you square it, you get 0. Great. 1 and negative 1. That's an interesting test because I gave it input where one value was negative and one value was positive. How does it react? Okay, it looks good. 5 and 5, okay, two positive numbers, not 0 though, okay, great. Negative 5 and negative 5, well, I gave it two negative values. How does it operate under that condition? And then I've got the floating point numbers there as well. Maybe I should have more tests here. You'll notice that for every input, I kind of basically gave it the same number. Maybe I should have given it like a 5 and a 7, just to see, you know. But this is probably good enough. Any questions about anything? But I'll get to the whole absolute value thing in one moment. Yes?
Can you do something where you have like the answer is greater than 0 instead of the specific case like 100? Because anything squared is going to be above 0, right?
You're right, but we can test for the exact solution, right? So it would be like saying 1 plus 1 is greater than 0, which is, yeah, that's correct, but you could get more precise. It is equivalent to 2. So you're not wrong, but why not get more precise? Other questions? Is your hand up? Not just a hair, just a scratch. Now this is something we're going to talk about in a little bit more detail, I'm pretty sure a little bit later in the course, but just as a funny little note, as an anecdote here. Computers suck with decimals. They're terrible with decimals. And there's an intuitive reason as to why they suck with decimals. But when you want to compare floating point numbers with decimals, you should avoid ever using equals equals. And that's because, well, sit tight for a second because I'm pretty sure I've got, okay, perfect. I do have the example here. I'll get back to this in one moment. All right, in the above examples, square of sum, test the number times under different input cases. And then you'll see like what happens when the input is 0, positive and negative, 2 positive, all negative. What happens when we have floating point numbers? That was my thought process when writing these tests. What are the possible little input cases? Maybe I should have had more, maybe it was overkill, hard to say. We look to capture the broad cases as it's not reasonable to test all possible inputs, right? That's ridiculous. Am I going to test 1 and 1 and then 1 and 2 and then 1 and 3 and 1 and 4, to infinity, and then 2 and 1, 2 and 2, 2 and 3, 2 and 4, and so on? That's ridiculous. You're not going to do that. So we want our test to be general, and you kind of have to think like, okay, if this function is right, it would be really weird that it worked perfectly fine for 4 and 5 and not for 5 and 6. Like that would be like, how could that happen? Someone would have to have gone out of their way to make that function incorrect. So, notice that the last test is a little different. If you're looking at that chunk of code and you're thinking, what on earth is it doing? Slow down. All it does is checks that the absolute difference between the two values is less than a specified number. The absolute difference is just because one of the difference is negative. I don't care if it's positive or negative. I just want to make sure that the difference between these two numbers are less than some threshold. And the threshold I used was 0.001. Let me ask you a question. Integers. What comes after 1? Someone yell out the answer. 2. Great. What comes after 2? 3. What comes after 3?
4.
Exactly. This isn't tough, right? Now we're going to deal with decimals. What comes after 1? 1.1? 1.1 comes after 2. You missed 1.01. Yeah. Kind of tricky, isn't it? It's actually really funny because if I were to tell you, you've probably never heard this before. Maybe you have, but it's likely that you haven't. Did you know that there are different types of infinity? Yeah. A couple people did. So there is what we would call countably infinite, where, okay, look, it's infinity, but I can count each thing on the way there, like integers. 1, 2, 3. I can put my finger on each one. And then there are things that are uncountably infinite, where you just can't do that. That would be something like with decimals, the real numbers. Because as soon as I say, okay, go put your finger on each real number. Well, what comes after 1? 1.1, 1.01, 1.001, 1.0000001, and so on. We can play that game forever. The point is, there's like an infinite number of numbers between 1 and 2 now. Or with integers, there isn't. There's 1, and then there's 2. There's actually more real numbers, more numbers with decimals than there are integers. That's weird, right? On one hand, it makes sense. On another, you're like, but it's both infinity. Well, turns out there's different types of infinity. And because of that, in our computer, we have transistors and whatnot. We have a finite amount of zeros and ones we can use to store integers. Eventually, we will run out of room. There is a max. Python's a little different. But if you have a 32-bit computer, meaning you have 32 zeros and ones, you can represent 2 to the power 32. What is that? 1, 2, 3, 1, 2, 3, 4 billion, almost 4.3 billion unique integers. Right? So I could start counting at 0 to 1 to 2, up to that. Or if I want to include negative numbers, okay, I can, half of that, but half of them are negative, right? Floating point numbers is a problem because there's just more of them. So how can I possibly, I can possibly represent that many integers. Don't worry, if you need bigger integers, it'll work just fine. We're talking a little bit more like classically speaking. I can only fit that many integers. But the problem is there's a hell of a lot more floating point numbers, so how can I represent them all? The trouble is we can't really very well. So the computer uses some interesting engineering tricks to represent floating point numbers, but the point is your computer is not actually capable of representing certain floating point numbers precisely. And I've got an example here. Nope. Somewhere here. Oh, there's a bug in my code here. Need to fix that. Wait, didn't I fix this already? There, okay, now it's good. If I say sum of squares, let's see. I hope Colab doesn't make me a liar, because sometimes it can do that. Oh, I didn't write sum of squares. Let me go get sum of squares. There. The correct answer is 19.36. That's the correct answer. But Python's saying, no, it's 19.3600000000000003. I may have missed a 0 or 2. That's wrong. We all know that's wrong. But this is the situation we're dealt with. So, programmers know the error you're going to have with floating point precision is always going to be something like with a bunch of zeros and some number. Meaning, like, what is the difference between 19.36 and 19 and that? It's so small. 0.0000000000000003. That's tiny. It's effectively 0 for what we care about. But if I try to compare those two numbers, Python's actually nice and it'll say it's true. But some other programming languages won't. It'll say no. The number 19.36 and 19.36003 are not equal. And you're like, but they are. Yes.
Why does Python say it's true but others don't? Why?
Just because Python has the luxury of being like a little newer and very agile, that they're like, okay, look, we know that it really means, so really when people are comparing floating point numbers, we know what they really mean, so it's incorporated. Someone went out of the way and had to do it. Other languages, maybe an older one, or maybe one that doesn't include a lot of extra bells and whistles, which is sometimes what you want, it won't. So the trick, whenever dealing with floating point numbers, if you ever want to check equality on floating point numbers, you don't. What you do is you calculate the difference between them and check if that difference is smaller than some threshold you care about. In my example I have, what did I say? My threshold was 0.001. No, I could have gotten a heck of a lot more precise. I could have said 0.0000001 and it would have been fine. And that's still a small number. But that's the threshold I cared about because that's the threshold I care about. Maybe I should have been a little bit more precise. Add more zeros. If you're going to ask, well, how do I know what threshold to pick? Pick something reasonable. But also consider the fact that, right now we're making programs that are like arbitrary, like, oh, write a program to do this, write a program to do that. But in real life, you're going to be writing a program, maybe you're writing a program for chemists. And your chemists want to do some comparison of the measurements. But the chemist's instruments can only measure up to the nearest like milliliter or something. 0.01 liters, right? So reasonably, I could check if the difference is less than 0.001 and be really happy, right? Like a tenth of a milliliter. There's no sense checking anything more precise than that because the instruments they use in the first place can't be more precise. Long story short, whenever comparing floating point numbers, you don't. You calculate their absolute difference, and then you check if that's less than some threshold. Pick a reasonable threshold. Any questions about that? It's a peculiar thing, but it's kind of neat, right? It's a fun little quirk of how these machines work, because it's funny. We have to disassociate computers and computing from those boxes in front of you. Those boxes in front of you are one specific physical implementation of a computer that has some physical limitations. But in a more abstract sense, a more abstract computer, one could conceivably construct a computer that doesn't have this issue. So this is a consequence of the engineering that goes into these things and how they work. But more abstractly, that limitation is just it shouldn't really exist, but it's a quirk of these. It's cool. I think it's cool. All All right, the above tests do a good job, but you may be wondering why I didn't test like 5, 6, or why we didn't test negative 1, 1. It's not unreasonable to include them, but presumably if it worked for the others, it's going to work for those as well. So let's write some tests for Celsius to Fahrenheit. So, of course, this is the Celsius to Fahrenheit function we had from the functions topic. It now includes the doc string, and it includes something called a, well, we'll get there in a second. Does anyone notice something funny about that function that you haven't seen yet? We'll talk about it in 2 seconds. No, nothing? You see something?
Has a float.
Yeah, what's up with that? And what's up with this? Huh. I'll talk about that in 2 seconds. So here are some tests for Celsius to Fahrenheit. 0, negative 40, negative 5, 30. I know that 0 Celsius is 32 Fahrenheit. I know negative 40 is negative 40. These are tests that I know what the correct answer is. So if I know what the correct answer is, my function better give the correct answer, right? I'm the one writing these tests. So I also check 30, which is 86, and then I do some funny other ones that might have some floating point issue, like 32. 32 degrees Celsius is 89.6 degrees Fahrenheit, but I don't actually check equality between those two. I check the difference, the absolute difference, and make sure it's less than a specific threshold. Similarly with 37.7777, that is 100 degrees Fahrenheit. But again, don't actually compare things that might have floating point issues. Do the comparison between being less than some threshold. Cool? So if you go and you look at your assignment and you see those chunks of code that say assert and everything, those are assert tests I wrote for you. You don't need to write the assertion test for assignment 1. I wrote them for you. That first function I give you, the load assignment 1 data or whatever it's called, the assertion tests aren't commented out because, well, that's for you to look at and like, well, the test should pass if you run that function. Those tests are there to show you, one, when I test the code that I give you that is complete, like the load assignment 1 data, and you run it and all the tests pass, that's a good sanity check for you that says, okay, the function he gave me is correct. Good. When you write your functions, what you'll do, because you write your function, the first question you're going to ask is it right? Test it. I gave you tests. Uncomment out the tests, get rid of the little hash in front of the asserts, and run it. If your function is correct, all those tests will pass. If they do, chances are you're right. It's possible that you're not, but it would be weird if you weren't. They're a really good way to ensure correctness. You can't guarantee, but they're very good at helping us figure that they are. So I gave you those tests, make use of them. If you're running it and it keeps giving you the wrong answer, well, you've got the wrong answer. If I get an email from any of you, I reserve the right for the following. If I get an email from any of you that says, I wrote the function and I know I'm correct, but the assertions are failed, I'm going to say, what will I say? I reserve the right to make fun of you a lot. Because you are correct. And you should know that you're not correct because your tests failed. If your tests failed and you're certain you're correct, you're not. Go back and look again. Now, I will put an asterisk saying, unless you accidentally change the tests, okay, that's a different story. Don't change the tests. So you'll be all set. Those tests are there to help you know if you're right or not. And it's good, it's important, because you'll notice in the assignment 1, it's like, okay, write this function, then write this function, then write this function that uses that function, then write this function that uses those 2 functions. If you know each function is correct along the way, you're comfortable using them in your bigger functions. Imagine writing a function and going, yeah, I think it's right, and then writing another function, and then it's giving you the wrong answer all the time. Where's your bug? You don't know. It might be in that old function or your new function. Alternatively, if you know this one's correct, you know it's correct, and you run this one and it keeps failing, well, you know the issue is with the function you just wrote using that function. Any last questions about these tests? All right. Notice the broad tests, input 0, when Celsius and Fahrenheit are equal, negative input, positive input, input is a float, output is a float, whatever. Cool. If you were writing tests for this function and end up having a few more tests that are arguably unnecessary, that's fine. Like if you are like a little extra cautious with your tests, great. If you write 54 tests for this function, don't. That's ridiculous. You don't need to. Now, knowing how many and what to test and how to test and which input is more of an art than a science. It's something that you will get a feel for the more practice you have with it. So don't feel bad if you miss a test, if you're writing your own test. Don't feel bad if you over-test. It's fine. You'll get a sense of it as you go. Just like learning a program. You get better at it as you go. You get better at testing your code as you go. Okay, I can't emphasize this enough. Writing code is only a small part of programming. If your code's not correct, you haven't done anything. You haven't solved the problem. I say solve a problem, you say I wrote the code. I say is it right? And it's not. You haven't solved the problem. You're wrong. You might as well have not done anything. There's an argument about thinking about tests before actually writing any of your functions. Let's not worry about that right now. And another thing too, if you're writing tests and you find that your functions are really hard to test, that might be an indication that your functions are too complex. Maybe you should break that function down a little bit more. Separate some of the things the functions are doing and then test them independently. You know, tests are really good at helping you reflect on your code. Sometimes the action of writing the tests helps you find a bug in your code even before you run the tests, because the process of writing the tests forces you to think about your function a little more. It'll force you to think of those edge cases. Now, this is a form of automated testing, but the correct way to write tests when programming is something called unit testing. And often programming languages have these systems that they provide to you for this really robust, sophisticated testing. We're not going to do that right now, but popular ones in Python are unit test and PyTest. We will talk about unit tests way later in the course. It's one of the latter topics. But right now, the assert tests are going to do the trick. They're great. They're a really good way to know if you're right or wrong. Now, type hints. Python does a decent job at figuring out what the types are based on the context and everything. We've seen this since like the first day of class when we talked about types. Maybe that was the second day of class. But the trouble is, if I have this code right here, and I know I've shown you this before. First number 1, second number 1, the output's 11. Well, that's not right at all. Well, it is right because you just concatenated 2 strings. Presumably, you wanted this function called add together to take 2 integers, maybe 2 floats, okay? Not 2 strings. But you gave it 2 strings, and Python was happy to take them. But the trouble is, this function, it operated exactly as it should based on the input. But you as the programmer had intended for the input to have some constraints on it. Constraints on the type. And what was the return type here? That 1, 1, that output, that's the string 1, 1. The output of this function should have been a number 2. So what we do is we add type hints to our functions. We say, you're going to take a parameter, we're going to call it A, it's going to be an integer. It should be an integer. So to do that, all you do, this is the syntax. You're not going to remember it from me talking about it right now, that's okay. It's in the course notes. You just go here, you say colon, I'll say float, because float's a little more general than int. Great. B will also be a float. And the output of the function, the return type, is also going to be a float. And you might say, but why not int? I could, but that's a little restrictive, because the integers and floats will work together. Like, floats are bigger than integers, but not the other way around. So there, I added my type hints. Now, and look, if I go to, look, I added the type hints. Remember the docstring thing, how I talked about how it'll say, like the docstring will pop up? If I say, oh, here, I probably have to rerun. One, okay. If I go back down here, add together, look, it's now telling me, no, add together A, and it wants a float. So now it tells you. So this is a way to protect a little bit. It's a way to communicate to yourself and other programmers, here's a function, it takes an input A, it's supposed to be a float. It's a way to communicate to the person using your function that there is a restriction on this input. And often what we would do, if adding type hints, we add the information within the docstring. And you do this by saying colon type of A is a float. Type of B is a float. And lastly, for return type, it's just R type. R type is a float. You're not going to remember these offhand, that's fine. But there, we now just added type hints. And it's a way to indicate to other programmers that this input is supposed to be a float. Now, I saw your hand up.
Oh, yeah, that's okay. I think
Oh, okay, cool. But type hints will not stop you from using the function wrong. I added type hints. Add together is supposed to take two floats, but I can still provide it with two strings, and it'll still give me back a string. So, the type hints are there as a form of communication. It will not actually make Python restrict anything. Python goes, oh, you know what you want to do. Other programming languages that are strongly typed, you specify the type, and if you give it an input with the wrong type, it won't run. It won't even like build your code. It won't even run at all. But yeah, we add type hints as a way to specify the type. It helps us thinking about the type of our data when we're writing the code. Right, it's going to be a float, so because of that, we use it as a form of documentation. It's not anything that's going to cause any restriction within Python. It's kind of like the constants, right? You make a constant, you can set the value, and after it's set, you're not supposed to change it. Great. But nothing is stopping you from actually changing that constant. The only thing stopping you is the public humiliation you will get from other programmers for doing that. Use your type hints. Whenever you write a function, add type hints now. Okay? Questions about type hints. This is another one of those things that it'll become second nature the more you practice. Every function you write, you add them, maybe you forget, oh, I gotta go back and add them. Okay, go back and add them. Great. In lab, don't be surprised if I give you a hard time. Oh, you forgot your type hints. Go add your type hints. Cool? Setting type hints, yeah. What you get, what I just showed you. What you don't get, it's not going to stop you from messing up. Great. Cool. Any questions about testing or the type hints before I jump to conditions? All right. Well, I'm going to, you're not like, I mean, you can do it if you want, but I'll give you 2 minutes to think about this. Using only what we've learned so far in this course. I want you to write me a function called Smush. It checks if the number, a number, is positive or negative. If a number is positive, the function returns half of the value of a number. So if I said 4, it gives me back 2. Great. If the number is not positive, so it's negative, simply return the number. So if I gave it -4, it just gives me back -4. If I give it 15, it should give me back 7.5, -15, -15. Write the function if you want, or just kind of think about how you would write it, but the trick is you're only allowed to use what we've seen so far in class. Who has a solution? That's what I thought. You can't. You can't do this with what we've seen so far. I mean, we saw the comparison operators, so you can check if a number is less than 0, positive or negative, right? You can go and be like, here, let's 5. And then I can say, okay, is print a number greater than 0. What? Oh, stop this. Yeah. Like, is a number greater than 0? True. -5. False. Okay, whatever. I can check, but I have no way to tell Python, well, given some condition, do this, otherwise do that. I can't yet. That's where conditionals come in. So like I just said, we can check if a number is greater than 0. That's easy. If the number is greater than 0, we know it's positive. If it's not greater than 0, it's 0 or negative. But I guess in our particular case, what do we do with 0? Do we just return the number, or do we return half of the number? Well, conveniently, half of 0 and 0 are equal. So it doesn't matter. So we can check if a number is positive or negative. But if I want to do something based on some condition, we need a new special type of statement called an if statement. So here's my function. I say, and look at all this fancy stuff here. Smush, a number, and it's going to get a float. And it's going to return a float. Look at those type hits. Return half the value of the parameter, a number if the value is positive, otherwise return the number. Great. Return types of float, some arbitrary number, half the number, whatever. I explained it all. Great. What does the code say? Well, here's how I wrote it. Start with the return value being set to a number. Okay, I've got a variable called return value. It's just like a placeholder for now. And it's going to be set to whatever a number is. I check if a number is greater than 0, colon, indent, just like a function, colon, indent. Everything I want within that if statement, that if condition is indented. If a number is greater than 0, return value equals return value divided by 2, right? So if it's positive, just half it and save it back in its own variable. Then, after that, return value. Great. Let's think about it. What would happen if I give Smush 10? Well, here are 3 tests. What should happen is if I give smush of 10, knowing what the function is supposed to do, I expect the output to be 5. Smush of negative 10 should just return negative 10. And smush of 0 is 0. Probably should have had a test here with a floating point number. I didn't. I'm bad. But there are some tests. So let's think. What happens if a number is 10? Remember, there's no trick. What does the code say? All right, we start with a number is 10. Great. A number is 10. Return value equals a number. So what value does return value have? Yell it. Come on, wake up. What? You said a number. What value does a number have? No, you're thinking too hard. Let's start over. Smush 10. So I'm calling smush with the argument 10. So the value of a number is 10. First line of code says return value equals a number. So what value does return value currently hold?
5.
No.
10.
10. We pass in 10. A number holds the value 10, and I immediately take the value of a number and set it to return value. It's just 10. That's it. Then I ask, is a number greater than 0? Is 10 greater than 0?
Yes.
Oh, don't say yes. True. So if the condition is true, we go in. So because 10 is greater than 0, I say, okay, return value divided by 2. What's 10 divided by 2? Where do I put it? Back in the variable return value. Thank you, one person. Then what do? Return the return value. I give back the 5. Great. What happens if I put in negative 10? All right. A number is negative 10. First line of code, return value equals a number. So what value does return value have? Wake up, people. Let's try one more time. Negative 10. A value stores negative 10. First line of code in there. Return value equals a number. What value does return value have? All right, we'll end today.